Selfies from space. So let's get started. With a little bit of background about me, I've always been kind of a science and a space geek for a long time. When I was about 10 years old, I got really big into model rocketry, and I wrote a big term paper on my hero, Werner von Braun. He was my hero for a while. Some people think he's the father of modern rocketry. So I was huge into that, and then later as life went on, I kind of got, out of that whole I want to be an astronaut, but I still do. I still want to be an astronaut. But it's just so hard, So I got into computer security and the hacking, so-called hacking. So I've always been into figuring out how things work, taking things apart and then putting my toys back together. I'm sure it annoyed my parents a little bit, but that's the price of science, right? So I've been a maker, so I want to thank the Triple Cities Makerspace. We have a makerspace in my town. If you don't know what that is, it's an organization that's dedicated to learning, and we also have these community tools that everybody that's a member can use, like 3D printers, and we have a metal shop, we have a wood shop, all this great stuff, which is cool because some of the tools are really expensive and I can't afford them. So we all pool our money together, and then we can all use these tools in a community-based setting. And another big resource there is the people. There's so many different people that come together to the makerspace. We have artists, we have engineers, we have musicians, we have all different kinds of people. And that's really neat because then if I don't know something, odds are somebody at the makerspace does know about it. So I just want to give a quick shout out to them. And I write for their blog. Their blog is at tcmakerspace.com. So if you guys want to check that out, I'm going to put a blog post about this on there eventually. So what got me into this? I'm a hacking nerd, right? What am I doing with space? Well, I had this thing called a software-defined radio. And that's this little guy right here. It's a USB radio, and it's about $20. It's pretty cheap. So I had this thing for about 6 months in my toolbox thinking, what am I going to do with this, right? So then I got onto Google, and I looked up what can you do with software-defined radio besides listen to the radio. And one interesting project that came up was downloading images from weather satellites. And I thought, whoa, that's really cool. And I had a few people along the way tell me, well, can't you just get images from weather satellites from the internet? And I was like, yeah, but it's so much cooler if you can get it straight from the satellite and cut out the middleman. So that is our SDR, and there's a big website for that at rtl-sdr.com. Tons of tutorials on there, all kinds of good stuff. You can also do other things with this, like listen to the cops. You can listen to, you can listen to airline pilots on here. You can view the tags that airliners use for their transponder codes if you have the right antenna. So it's a neat little gadget, and definitely got my 20 bucks worth. So speaking of antennas, so that's kind of the key to this whole thing is our antenna. And the antenna has to be tuned to what frequency we want to receive. So the way that works is by something called resonance. This is how radio works, is resonance. It's kind of like when you have a tuning fork, right, that's going off, and if you bring another tuning fork near it while the other one's vibrating, the other one will eventually start vibrating. This is essentially how radio works. We send a wave down at a specific frequency, and then it goes into our antenna at that same frequency and vibrates, and then we take out the data. So these satellites that we're getting, they're called polar orbits or sun-synchronous satellites. That means they go overhead from horizon to horizon. They don't stay in one spot. I think there are some weather satellites that do stay in one spot that are geosynchronous. Unfortunately, though, a lot of the ones I saw are near the equator. It's probably easier to maintain an orbit near the equator. So I think my antenna is probably not big enough to reach them guys. I'd have to move to the equator, which sometimes in the wintertime I want to do that. But so another thing we have to look at is the signal from our satellite is rotating because it's going around the Earth. So the signal's not just coming straight down, it's also rotating while it's coming straight down. So that's something called circular polarization. And so we need to take that into account when we design our antenna also. So there are certain antennas that work for this circular polarization. One of them is a quadrifilar helix. And if you look online, a lot of people swear by this antenna. Unfortunately for me, though, it looks super complicated to build, and I just don't have the time yet. Maybe eventually I will build it, but it's the way it works is it's all, well, let me pull up a picture and you can see what it looks like. Oh yeah, I don't have internet. Fail. Okay. My bad. Well, anyways, we also have an antenna called the double cross, and that's where we'll take two poles. So these will be our poles, and we'll make a cross out of them, but then we take two more and we make a double cross. So you'd have something like, look like this kind of, that kind of deal. So that would be your double cross antenna. And these antennas, they have something called a radiation field, and that is kind of a complicated math that goes into that, but it all goes back to that wave and when it hits the antenna and how that wave is intercepted. Then we have a turnstile, which is kind of like the double cross, but that one goes instead this way. The turnstile is like this. That would be a turnstile antenna. And then finally we got to my favorite antenna because it's very simple. It's called the V-dipole. So that antenna is just two poles and they're like this. They make a V. So we need our antenna to be tuned. So what does that mean, tuned? So that means that I can't just use any piece of wire. It has to be a certain length to match what frequency we're trying to get. So I found this guy online that plans to make this V-dipole antenna from a ham radio operator, which I'm going to get my license pretty soon for ham radio because it's pretty neat. You can do some cool stuff with radio. And according to his plan here, he has 53.4 centimeters as one of the legs, which is the length of one of these guys. So that seems awfully specific, right? Why would he need that specific length? Well, it turns out if we take the speed of light and divide it by our frequency that we want to get, we'll get our wavelength. And these dipole antennas, the way they work is we need half of a wavelength for the whole antenna, so it's a quarter per pole. So a quarter of our wavelength, which is 2.18 meters, is 106 centimeters. That's half. So we take 106 divided by 2, that'll give you your quarter, so that's these guys, 53 centimeters long, about, roughly. That's to make sure that they resonate at that same frequency and pick up the signal that we want to get. So our other materials are, I'm using wood for a base here because it's cheap and it's a great insulator. And like the chart said, we want 120. 120 is optimal because we want to catch the wave in between here. That's what's going to happen, is we're going to get half a wavelength in between these guys on both of them at the same time. Then we're using a 50 ohm coax cable. This is not the same as your TV cable. That's a little bit higher of an impedance. So impedance, yeah, that's something we need to worry about also. So this is 50 ohm cable that I got from Amazon. And impedance is kind of like resistance. So we need to match up the resistance of the electrons that are going through these poles in order to be able to get that signal accurately. So one time I got some poles that were a lot thicker, and I thought, whoa, thicker, more electrons, maybe I'll get a better signal, right? But guess what happened? I didn't match the impedance, and I didn't get any signal, so it turned out to be a big paperweight. All right, so then I'm using wood screws to attach to the base there, and ring connectors on my coax. And originally, his plans called for something called a chalk block. Well, I had a hard time finding a chalk block at Home Depot or Lowe's, and I really wanted to get into this right away. So Home Depot and Lowe's they know me by name, I think, now. So the way this works is we take our cable, and I splice out this coax cable, right? So I get the center element, and I get the mesh around the outside of the cable. So that's your two poles, and we're going to hook that up into our poles here. Alrighty. I haven't found a better way to connect these yet. But maybe one of you guys could help me out with that. So, okay, there we go. So now I have connection to those two poles that are each one is a quarter of our wavelength. And this allows us to get that right-hand circular polarized signal. So one wave is going to hit here, one wave is going to hit here. We combine them, and then we get our gain from that. All right. So the V-dipole, it looks really simple to build, and it is. And part of you is like, well, how can such a simple antenna pull any useful data? But it can, it really can. So let's talk a little bit about the software that we use. So you have to install drivers for this software. Oh, you got a question?
Yeah, would you mind if I ask you just a quick hardware question before we move on?
Sure.
It's just two, thanks. So the first one is, what is a chalk block? Why didn't you need one? And then the second one is just about the shapes, the antenna shapes that you're talking about. What are the sort of advantages of choosing a more complex shape? Because I assume that everybody would just pick the simplest shape and the other ones wouldn't exist if there was like no differences between them all.
Oh, there are differences between the antenna shapes. Yeah, that's for sure. So the quadra helix one is very complicated to build, but it makes it more omnidirectional. You don't have to worry so much about which way you're pointing. This guy, you want to have your satellite in between these two poles, so you kind of got to track down where it's going to be in the sky, and you got to go with that. The double cross antenna is a little bit more omnidirectional, and you won't have to worry about tracing the satellite with that as much, but it's a little more complicated also. Since there's two more poles, I need another cable, right, to hook into there. But because of the math, I can't just pick any size. Again, because of impedance and whatnot, there's a calculation for a specific size of cable to connect those guys. That way, when the signal hits here and the back guys, they don't collide and cancel each other out. So it makes it like delays it, I guess, a little bit to make the amplitude bigger. But that's a great question. And the chalk block is, I think what the guy used was, it was like, for some electrical systems, like a grounding bar. So it looks kind of like that, like a grounding bar, something you would just connect wires into, not necessarily poles. So I found these guys, which are kind of grounding, they are grounding bar type apparatus that I found at Home Depot that seem to work and do the job. And also they're aluminum, so they're conductive. Yeah, also this should be aluminum. The bigger poles that I tried before were copper, so I changed the material, so that also changes the conductivity, right? And that impedance again. So yeah, I could pick up FM radio on that thing pretty well, but when it came to the satellite, 137 megahertz, I just couldn't get it. Couldn't see it. No matter which way I turned it, it wasn't working. And I was like, oh, that's why, because those electrons, they just can't seem to get through on that tiny wire from the huge conductor, you gotta match it down. So you almost need like a transformer. I don't know if you guys are old enough to remember, but on TVs they used to have this little transformer thing with two wires that would come out and hook into your TV. Then the other end was coax, and that was to transform the signal to the right impedance to match your TV, which now TVs are all digital, so it's not like that anymore. But so software we're looking at for the software-defined radio, you can go to that website again, rtl-sdr.com. There's a quick start guide there. It's a little bit funky to install the drivers, but it's not that bad. Their quick start guide has pretty detailed screenshots, so it's pretty good. So the thing I'm using Windows, unfortunately, so I'm using SDR Sharp. I am more of a Linux guy, but unfortunately, PowerPoint and all my other line of business apps I need to run on Windows. So we're using that, and we're also using a program called Orbitron. So that's the second part to this is you need to know when the satellite's coming over in order to intercept it. There are a few programs online, and unfortunately, they vary a little bit in their times, which is kind of weird. You'd think they'd all be the same, but they're a tiny bit different. But it also has to do with your coordinates, your GPS coordinates, where you are. So you need to know that, which you can Google your coordinates and put them in. And then you get a time. Usually it's, these guys are going super fast, so it's only going to be 10-15 minutes before it's out of sight. And not really sight, but like radio sight. So the satellite could be over, like Texas, and you could still get a radio signal from it because it's so high up there that it's still going to reach you, right? Because they're about, I looked into that, they're about 515 to 520 miles up. So pretty high up, and they go pretty fast. So we're going to need something to predict when it's going to go by. So there's this handy program somebody made called Orbitron. And you can download something called a two-line file from online. And that gives some numbers for the program to work with. And it throws it into calculations to figure out when the orbit is going to pass by you. And you can set different settings, like how high you want it to be in the sky before you have it alert you or predict that. We'll look into that a little bit later. I'll do a demo. And to capture NOAA stuff, we're going to need an audio program. So NOAA satellites, they use an analog signal. So it's actually a beep. You'll hear a beep, 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 beep. And so we need Audacity, which is free, to change the sample rate. Because unfortunately our SDR Sharp doesn't sample at the same rate that the program we're going to use to decode. Which is the next thing. We need demodulate and decode programs. So we have WX to IMG, app decoder, LRPT decoder, and smooth meteor. So let's take a look at the satellites real quick. So that guy on the right there, that's the Russian satellite, Meteor M2. So that's a sample of what it looks like. And someone else said earlier, don't they run on different bands? Yeah, that's true. So you see there's an SM band antenna, there's an M band. So they're sending data back on different radio frequencies. So they use different antennas and different bands for that. We already said these are polar orbiting satellites, so they're not geosynchronous. And the ones you can get data from that are active are NOAA 18, NOAA 15, NOAA 19, and the Meteor M2. The Meteor M2 is my favorite. I get really good pictures from that, so I really like him. Plus, he uses a digital signal, not an analog, so it's a little easier to capture, and you don't have to listen to beeps. It sounds, if you listen to the signal, it just sounds like a hissing. So, but if you can see the hump, I'll show you in our demo here what it looks like. Then you can decode and you'll know you're locked on. So the NOAA guys use APT, which is automated picture transmission, and the Meteor M2 uses the low rate picture transmission, or LRPT. So how does this work? So radio works with something called modulation. Modulation is varying the frequency or the amplitude of the wave to get your data out. So say we're sending ones and zeros. Let me move, how do I move this thing up again? Just move it. Oh. Okay, so let's say this is like our signal line right there, and we want to send a 1, so we'll go up for that, and we'll send a 0 like that. So we could do this, right, all day or whatever, but eventually it's not, we stay on the same frequency, it's just not going to work for us. We need to do something called modulation to vary the signal or the amplitude or the modulation, or sorry. So amplitude is how high up this goes. So we can vary that. We can have the same frequency, but we can just make these waves smaller or bigger. And that's how AM radio works. So AM is amplitude modulation. And it's an analog way to do it. So APT actually uses this analog way, this AM modulation, to send the pictures down. And LRPT uses quadrature phase shift keying. So that's a little bit different. That one, we have, let's say we have like a sine wave, and then we have like a cosine wave. And you'll notice they're out of phase by like 90 degrees. There's 90 degrees difference in the phase. So when we add those together and make one signal out of that, then we can send that signal. And if we demodulate it, we can get these two waves again, and then we can get our 1 and 0 that way. But quadrature is 4, right? So instead of being just a sine wave or a cosine wave, we need to look at it as polar coordinates. So polar coordinates, right, we have stuff over here and here. So this right here would be like 90 degrees. And over here is your 180, right? 270 over here. So when we get out of phase, we can always pinpoint where our data points are according to how far out of phase they are by what degrees. And because of that, we can send 2 bits at a time instead of just 1. So we could have 0, 0, 0, and we could go all the way up to 1, 1, 1, 1 with this scheme. So that's why I get a better picture, a better resolution from the LRPT or the Meteor M2 satellite. So that's kind of what we just showed right here, right? Our AM modulation. So we vary, right, the amplitude of the wave, and then we can get our data out that way. And yeah, quadrature phase shift keying, we looked at that. So you'll see that wave over there on the left. There are differences in its phase, and according to that, that's how we can get out our data that way. And that correlates to the polar coordinates, which you'll see when we decode some data from that in the demo. So let's look at that now. Let's look at the demo now and see what we can get out of here. So let me go to here. So SDR Sharp allows you to record files, and then you can replay them. I don't know if you can hear this, but there's some beeping going on here. And that is an apt NOAA satellite. Maybe I have a better one you can hear.
It's still showing the power.
Oh. Okay. So I don't know if it might be hard to hear. I don't. But there's a beeping noise. So one advantage to tracking the NOAA satellites is you'll hear it. So and I recommend if you're tracking a NOAA satellite, maybe headphones might work for you better, so you can hear a little closer and adjust your bandwidth. But it almost sounds like a fax machine, right, or a modem, which it kind of is. It's doing the same kind of thing. It's just sending ones and zeros between the beeps and the not beeps. It also sends telemetry data through that clicking noise. Let's see what. So here's an example of a NOAA picture. So that beeping noise comes out to be something like this, which is kind of staticky, but and it bases the map on the telemetry data, which is those bands on the side there. You'll see. So the program reads those, and that tells you where it is according to that. So this is another apt picture. It primarily just picks up clouds. You can't really see too much else from there. So this was my first one. This was my first one, and yeah, it came out all staticky, right? So, and actually, the first time I went out to track a satellite, I didn't do enough research on the satellite, so I went out there and I was all excited. It was raining, and I was like, "Screw it! I'm out here. I'm gonna listen to a satellite." And I put out my antenna, and I turned it on, and I was there at the right time, and nothing. I didn't see a signal. And I thought, well, that's weird. It was supposed to definitely be here, right? Turns out the satellite I was trying to intercept was damaged, and its transceiver was broken, so it couldn't talk to me anyway. So that was kind of a little bit of a turnoff, right? But I kept at it, and I got some great pictures afterwards. So let's take a look, I guess, at our other guy here. So these pictures here came from the Russian M2 satellite. This one's from this morning. Oh, yep.
Did you get these from this antenna?
Yes, this one came from this antenna this morning. This guy right here. Yeah. And I was super excited about this one because you can actually see the middle of the United States. So usually when you capture data from these satellites, all you can get is what they're giving you from overhead. So it's kind of like a scanning mode. They're scanning the Earth, and you're getting that data in real time, which is pretty cool. So if you could zoom in, which I'm way up there, if you had the chance to zoom in, which these cameras aren't that great anyway, but you would see me outside with my headphones on, trying to do this. Yeah, since the satellite's so high up, I can get further than where I am locally and get these pictures. So this one came from Russian M2 this morning. Super excited about that one. Sometimes they'll be on the other side of the country, and they'll be like in the ocean. So that one's like in the ocean. Some of these black lines, you'll see some black lines. I might have lost signal a little bit temporarily. But also I read online there's an issue with the Russian M2 transmitter. Every now and then it just stops working. So you'll get a black line anyway, which is odd. So like this picture here, that one main black line, that was not my fault. That was Russia. Thanks, Russia. But still. Yeah.
Is there a certain frame rate the satellite sending picture? That's transmitting that?
There is. I'm trying to think of what the resolution is. I think I had it somewhere. I had the resolution of what it was. It's kind of not that big, so like you can tell you can't see any man-made structures because it's so high up, and the resolution is not that good. I think it's like 1 pixel is like maybe 1 meter, maybe, if that. Probably not even that.
Is there a limit to how many pictures they're taking per minute or something?
That's a good question. I'm not sure. Most of the guys that I've captured, they're scanning. So they're not really taking one picture. They're sending a continuous stream of data like, hey, this is where I am. This is This is everything I see. This is everything I see. That's kind of how they work. They're not going click, click, right? They're just continuously pulling data up from up there. Some of the NOAA satellites, though, I think they do take pictures, stitch them together, and then at certain frequencies and times, you can get that whole image. So that's another good one. This has been I've also learned some geography doing this project too, because then you're like, well, where's this, you know? And you're like, I need some major landmarks to find out, right? So the Great Lakes are great for me to see. I'm like, oh yeah, there they are right there. And I think you guys, New Jersey, right, is right off that tip right there, right? Right over here somewhere?
Yeah, around that. Right.
I'm excited for summer too, because it seems like every time I pull an image from New York, it's always cloudy. Always cloudy. So yeah, this one took a little work, right, to figure out where it is. But, and that's the other great thing too. These guys make different passes. I get different angles of the Earth and such. So it's pretty neat. That's the Great Lakes again.
Since you're capturing these images as they're being taken, they will always be of the U.S. and the areas around the U.S., correct?
Correct. But if I traveled to another place in the world and I knew when the satellite was going overhead, I could get a picture of that place. Or if I had an antenna high enough to reach the satellite when it was in another area, I could get a picture that way. Or if I could boost the signal somehow, which is this little boxy thing here, is actually, it's a filter and it's a preamp. So the signal goes through this box, it filters out like the FM data we don't want, and then it boosts the signal that we do want, which is around 137 megahertz. These satellites all operate around there, they're close. Russia, M2 is 137.9 megahertz. The NOAA guys are like 137.1. One of them is 137.5. So they're all in this 137 range. So let's take a look at how I get these pictures, right? Where is SDR sharp? Here. All right, so this is SDR Sharp. This is the signal analyzer that we're using to capture these signals. We have the option to record them and then play them later, which is pretty neat. Or we can do things, there's a plugin over here to demodulate on the fly. And I just started doing that recently. So let me change this to an IQ file, and then we'll pick one up here. All right. And then if I hit play, so here's playback. Here's what it looks like, or what it did look like when I was out there. So you can see we got some major things happening over here, right? Over in this area. So, and that's 137.9 if you'll take note there. So that is Russia's M1. And when did I record this? Maybe like 2 days ago. There's something funny happening here though. Because if you'll notice, see there's some red stuff over here toward the right of there. It actually lined up. There was a NOAA satellite at the same time around the same frequency that went overhead. So it was kind of cool that I could actually record both signals at the same time. And let's see if I turn this on. There you go. And you just hear a hissing, and that is the digital signal. But if I zoom in on right here, this is bandwidth. I can change the bandwidth. And you can hear a faint beeping when we try to zoom in more on it. There you go. Hear that beeping? Kind of? So that's the NOAA satellite beeping, just like that. Yeah, I can zoom in here. And you'll see, if you see these waves, they're going up and down. So that's our amplitude modulation happening right there. All right, but you can tell even if I adjust this bandwidth, there's still, you can hear some hissing in there, and that's that noise, right? So that makes that staticky picture that we had earlier. So let me load a different file that doesn't have that, and then we can see. There you go. So that's Russia, and you're not going to hear any beeping. But I have this plugin down here that'll demodulate on the fly. So if I turn him on, then you'll see down here, you'll see our polar coordinates right there, right? So that is this guy right here. So then we're trying to find those signals that are inside that carrier wave, which is actually, it's a band. So there you go. You'll see over here, it says locked, signal locked. So now we're locked on to whatever that signal is. And I actually have to make this output file. So I'll just hit start here and we'll see. And you'll see it's writing data there. And the way this works is it's that whole, so this is a bandwidth, right? From here to here, from left to right on there is a bandwidth. And it's about 120 kilohertz there. So the reason this works is we have a carrier wave that's at 137.9, right? 137.9, that's our carrier, but we're in a band here, and it's actually adding to the cosine wave and the sine wave together. So you get something over here that's less than 137.9, and you get something over here that's more. So these two waves combined give you what is being carried in your carrier signal. And that's why we need a lot more bandwidth for this guy than the NOAA satellite. But we get a lot better picture, right? All right, so I would run this out in the field. I would have my satellite hooked up, my antenna hooked up to this guy. Right, so we have the coax cable, you just screw it onto there, and then plug that into the PC, turn this on, and this is what we would see. And then we can use this demodulate plugin for SDR Sharp to make something, it's called an S file. It will write an S file out. So you'll actually see that in the same directory. There you go, you'll see there's an S file there. So that is our demodulated data. So then we use another program to turn that into a picture. So we use this M2 LPTR decoder, which is Russian. There was another program, but it was all in Russian, and I didn't know how to speak Russian, so couldn't use that one. Over here you'll see there's symbol rates. It's always going to be 72 unless they change something for a test. But, everything I'm seeing has been 72. So then we pick our S file here. And you'll see up in the top left corner here, it's doing this polar stuff again, the polar coordinates, to find our demodulated data. So that bit we just ran just now, it wasn't enough to really make a big picture. It's just that little chunk, which is that big, just barely the Great Lakes. And it was on the 30th, so that was today. But normally I get a lot more out, right? And you'll see there's 3 channels that Meteor M2 uses. One of them is infrared. I think 2 of them are infrared actually, and then one of them is more land-based camera. And these settings down here, the red, green, blue, we can take those colors from these different channels, and when we combine them, which is this generate guy, that combines all 3 channels into one picture. And then you can save that picture off as a JPEG or a bitmap. JPEG is a compressed file, so if you could go to bitmap, you'll get a little bit more information because it's not as compressed as a JPEG. All right, now let's take a look at decoding that other guy, the app picture. So from that one, we're going to need to use Audacity because the sampling rate that was used by SDR Sharp is not the same as what the program we're going to use to decode it is. So let's see. We want this guy. There we go, so you can see. You can hear the beeps a little bit. Still some noise. A lot of noise there. I think there's a lot of noise here. So I can cut out all this noise right here. Also, our program is going to be expecting a mono track. Whoop.
This is only needed for the analog signals?
Right, only for the analog signals this is needed.
Which is NOAA satellites and not Russian satellites?
Correct.
Okay, gotcha.
So we'll need to go and mix this down to mono, so one track. And then we need to change our sampling rate, so you can do that right down here. It's expecting it on this 1125 hertz. So if I pick that and then just export this guy as a WAV file, and sure, plug it in there, sure. And that resamples the entire file so that other one can read it. We can also do something here called normalize. We can make the peaks a little bit bigger. Makes it louder. But yeah, you definitely don't want a lot of noise when you're doing the analog stuff. So I feel like it's harder to get a decent picture, and it's a lot easier just to do the digital guide from M2. So then we can use this program, WX to MG, which is freeware. And it takes a long time to load for some reason. Because it has a little counter there. All right, so then we can open up our audio file. So let's find out where that is. Probably this guy. So right now it's going through that file and it's trying to listen to those ticks and the beeps. And you're not always going to get a good picture. So it guesstimates which satellite it corresponds to according to the time on your file. So that means you got to edit it kind of quick when you recorded it, unless you change the time on the file with Linux, like using the touch command. You can do that. Or up here you can manually pick which satellite it is, and it will try to match it up to whatever pass it was. That's purely just for the map. Let's pick a different file because this is not fun. Let's find a better WAV file. I think I had one in here. Sound. Let's try edit. There you go. So this is a little better one. This one was Wednesday. I think Wednesday I grabbed this guy from NOAA 18. And so you'll see, this is mostly for clouds. You'll see over here a lot of cloud stuff. This guy right here, this is the telemetry. So this kind of tells the program where this picture is being taken and some coordinates. And then it matches it up and it overlays this map on top. Yeah.
What are the gray bits around the clouds?
The gray bits where?
So you know how you go to the eastern ocean part, and then you've got your cloud bank, and then around that there's some gray stuff. So what is sort of the signal? What in the signal causes that gray part?
So are you talking about Like this kind of thing? This guy?
No, it's in the actual picture. It's just like right along the clouds. So like there's the blue ocean, but then there's that band
Right.
of gray in like the top half.
Oh yeah, yeah. That's just because I guess the program couldn't decide what color to make that, but it's most likely clouds covering there. And yeah, you'll see these lines here are not there from the satellite. The program puts them on there. So let me change a setting and we can see what it looks like raw straight from the satellite. So if we go up here to normal in the enhancements, you'll see, okay, let me turn off the map. Hang on a second. Disable map, here you go. So that's what you'll get straight off the satellite. It doesn't really have the map. The program figures that out by that telemetry data, which is the gray stuff over here that kind of looks like a TV test pattern. That's the telemetry data, and the program uses that data to figure out where the coordinates are and to line up that map overlay. So yeah, mostly with the NOAA guys, you're going to see it's just two channels, and it's one's an IR, and the other guy's is purely a different spectrum. And in this program, there's lots of different options we can use to try to enhance our pictures. So here's where you can get the color from. It does this fake color, so it guesses at it. But we also have some fun stuff, like you can run a thermal analysis on it, so you can tell what's hot and what's not. There's lots of other enhancements in here. I'm curious about this hurricane one, but I guess we don't really have a hurricane happening to find, so I don't know. False color. Yeah, there's lots of different options, but it tries to combine those A and B channels in this guy to make one picture. And you'll see it has the data up above it, what time it was. It's NOAA 18, and the channels that's at, and which way it was going, north or south. That's important sometimes because you might have a picture that's flipped upside down. So then when you're trying to do your geography and say, where the heck is this? You might have to flip your picture over and then compare to like Google Maps and you'll be like, oh, okay, that's where it is. So let me show, I think I have, one of the programs I was using online, let's try to find it here. But yeah, here's NOAA, and you can see there's those Great Lakes again, right? So I'm glad those are there, so I know where this is. But you can see this cloud cover. It almost looks like the NOAA guys are up a little higher, which they are, than the Russian M2 satellite. There's a good pass of the East Coast. So you can see Florida. And there's New York and all those clouds. So at nighttime, interesting enough, at nighttime from the Russian M2 satellite, you can't generate a color picture because the sun's not there and it doesn't, you know? So for a while I was like, why can't he do this? Why can't it just put in color for me? And I'm like, oh yeah, the sun's not there, so that'd be why. And it also is so high up you can't see lights or anything. I was wondering about that myself, like maybe you could see lights from the city, right? But no. There is some weird stuff though out by the ocean that you can't see, which is kind of strange. So there's New York at nighttime, right? And you can see the clouds. And yeah, here's that stuff I was talking about in the ocean, which shows up on Google Maps too. So I don't know, you must be able to see. Maybe this is the sea shelf, maybe? But because they're infrared cameras too, we can pick up all these weird different things. So there's the Finger Lakes over there. We're like over here somewhere, right? Somewhere over here.
Move it up a little bit to the right.
There's Long Island.
Yeah, that's exactly.
New Jersey.
But yeah, you can see this weird stuff, right? That's always out by the ocean, and it's always there. This weird, like, dark colored things. At first, I thought I was doing something wrong, but no, it definitely sees that. I don't know if it's a deeper part of the ocean, and the camera picks up on that, or what the deal is. So here we go. Here's a picture. So the online webpage that I was using, I think it's called TrackSat, showed a path, right, which is that blue line of the satellite that was passing over. And then this guy on the bottom is the picture, part of the picture that I got from that pass. So that helped in identifying, although you can see the Great Lakes and everything, it's easy to see. If it's not all cloudy, you can tell the Earth masses, right? Here again, if we had the ability to zoom in, you would see me out there waving. But it gets all pixelated. So yeah, this website can tell you, it can predict when the next passes are going to be that are over your location, latitude, longitude. Yes?
So these satellites orbit the Earth every hour and a half or so. So
Yes.
Can you expect to get at least one pass per day?
At least one, yeah. You could probably get more than one. I see with the M2, which I like to track him a lot because I get great pictures from him. So I could get 2, maybe 4 a day of him that are decent. There's some passes where you're just not going to get anything. Either he's too far away, or there's clouds in the way, or who knows what else. But if you can, the closer that line is to where your latitude and longitude are, the better your chances for success are. And this tool will show you, and you can see over here and see how it says radio. So even though it's not a visual pass, like you can't see the satellite, but it's there and its radio waves will be within this area on the map. There's another great one of the Northeast. Another nighttime pic. Some of them just don't come out good. You're like, well, okay, but you gotta keep trying. So here I used a different enhancement on this guy. Oh yeah, he's hard to see, but a lot of cloud cover. And there's that dark thing in the ocean again. You're like, okay, right down here. And you can see the swirling of the storms. Sorry, flat earthers. And yeah, I actually had a guy, I posted a pic to Instagram, and I said, you can actually kind of see the curvature. And this guy posted like, you can't see what's not there. And I was like, and here, this is the first Meteor M2 picture that I ever decoded. And it took me like 2 weeks to decode, but it finally came out pretty decent. You'll see right there, that's that malfunction that happens occasionally. But otherwise, this is probably my best picture, and it was like my first picture. And this was right before, I don't know, we had a large snowstorm like the day after this happened. So probably all these clouds here just dumped on us. And you can see, sometimes I think you can see snow on the ground too. NASA's actually running a program right now. You can download an app to your phone and take pictures of clouds and then send them the data they want to know, because they're trying to find out the difference between a cloud and snow on the ground from their satellites. So you should look that up. Yeah.
Are you able to take a picture anytime you want?
No. I'm limited to the time that the satellite goes over. So one time I stayed up till like 4 in the morning because there was a pass at 4 in the morning, and I was starting to get obsessed with this. And I did it, and I got a decent picture or whatever. So yeah, you're kind of limited until that pass happens or whatever. And I was late to work one time, but I got a great picture. And yeah, you can't do it anytime you want. But, so there's that first that first signal, that first day, and you can see there my signal to noise ratio, it's huge, so I got a lot of signal right there. And this waterfall graph on the bottom changes colors according to the signal strength. You can see it's really red there. And then you can see these other guys, which I have yet to figure out what they are, but they are related to that satellite, perhaps sending different kinds of data on other frequencies. And I haven't figured out how to take that down yet. So there's this antenna that was that first day out in my backyard, and I got a good picture from it. So, all right, let me go back into here, I guess. Go back to where we are. So, some hints and tips. So you want to try to find a spot that's away from interference, electrical interference, physical interference. If you could have a good clear view of the horizon of the sky, that will help you out. You don't want to do it. I tried to capture an image one time next to a power station. That was a bad idea. A ton of interference. Didn't get a good picture. So my backyard is good because there's not a lot of radio waves out there other than my Wi-Fi, which is pretty far inside. So yeah, if you can get away from other signals, that will help out. If you could get higher up, that would probably help you out too, because then you get less interference and a clearer shot to the satellite. Also, we can try different antenna types. Yep.
So like New Jersey has like Watchung Reservation, for instance. It's like they're like small mountains, but they're kind of mountains. So if you were to like hike one of these up there, you might get like a really good clear signal.
Yeah. Oh yeah, especially because you're away from all these other radio signals, right? That we use every day, like that are in our pockets. Like this is giving off signals, and like your Wi-Fi and your computer and all these devices are just giving off signals. That's the other cool thing with this device is we can analyze all those signals. There's tons of information just flying through the air that we can't see and we don't know about, but if we hook up one of these guys, we can see. And that brings up a good point. I have an electric fence in my backyard, so I can hear it clicking. And if I point my antenna just the right way, I can pick up, that signal on the waveform analyzer there. So yeah, it's very, very interesting stuff. But yeah, if you can, and these are portable too. You can, once you take this out, I'm thinking about trying to come up with some kind of portable device antenna to use, but then I need another hand free, so I'm trying to figure that out. But yeah, you can definitely pack that up, and if you go on a hike, you'll probably get a decent signal up there. And then the last guy, we can use this signal or amplifier to cut the noise. And you can buy that online. I got this guy online at airspy.us, and I think it was like $50, but it does help. So. Like today, I was able to get that signal from like the mid US, and I couldn't get that before. I couldn't get that far before, so that box definitely helped out. And it's USB; it's powered by USB, so that's another added benefit, bonus. But yeah, it's got to be powered right to amp up the signal. You can't get something for nothing, unfortunately. No free energy. And then I had my questions, if anybody had any questions. Yeah.
How do you physically align, especially because you're using, what is it called, a V-type
V-dipole antenna, yeah.
So, how do you sort of figure out which orientation it needs to be in to be lined up with the signal?
That's a good question. Okay. Oh yeah, we didn't look at Orbitron, did we? Let me bring up Orbitron and take a look at that. So this is our satellite prediction software. And you'll see there's all these satellites over here you can track. I have all the weather guys turned on, the guys that are active. NOAA 20, by the way, that was the satellite I tried my first attempt, and it was there. It just wasn't talking. Unfortunately, it's not active. Some of these NOAA satellites are kind of old too. And the Meteor M2 was launched, I believe, in 2007, so he's relatively new. There's another one though that's coming out pretty soon. So excited for that. But yeah, if I go over here to this prediction tab, it'll take those 2-line entries, and based on that, I can predict when the next pass will be. So here's a NOAA 18, and it gives you this kind of circular thing, like you should be able to get something that's within this circle in the range. So how do you know where to point it? So this guy is coming south to north, right? And he's on the east of us. So I would point the antenna with these guys to be southeast. So I want to pick up that guy kind of in the middle of here. And so he's going to be setting down his signals, and I want to catch them in between these two arms right here, these two dipoles. So you might have to move your antenna while it's going over too, while it's going overhead, because it's going to pass you. Yeah.
Does rotating your antenna while you're recording signal affect it in any way?
Yes, it does. Sometimes it's a good thing, and well, sometimes you have to. You have to rotate it if you're losing signal. Sometimes it will take away though, and that's when you'll get those dark black spots in between if you lose data when you move the antenna. But sometimes you have to do it to track the satellite. There's actually an option in this program too where you can, if you had a motor and you had some kind of system where you could drive the antenna to follow the satellite, which is something cool. There's another program I think that does that too. Oh yeah, we forgot to talk about Doppler also. So there's another thing with the NOAA satellites that you have to worry about is something called the Doppler effect. So they might be transmitting on one frequency, but because they're moving and they're moving so fast, that frequency gets changed a little bit. It's kind of, so the Doppler effect is when, if you've ever been at a train stop and a train's going by and you hear it go whang, and it like changes its pitch a little bit, that's the Doppler effect. And we see that as well with these NOAA satellites. So you might have to actually move your signal off of what it's supposed to be transmitting at. And this program will do it for you too, with a driver, or you can do it manually. But yeah, we can look here, and this will tell us the angle it is, right? Over here is elevation. Anything pretty much over 10 degrees you should be able to get, you should be able to see. So this, the middle guy, the guy in the middle is probably peak to what you'll get. And it gives you a time right there, and it's military time, so I'm learning military time also, doing this project. If you can't get a decent signal by that middle guy, you're probably done. But yeah, the closer this pass is to where you are, the better your chances, right? Yeah, a lot of them, they'll be on this eastern seaboard. Some of them you'll get that are, there you go, like in the middle of the country or Cuba. I've gotten stuff from Cuba before. And maybe if I tune my radio right, I could get Cuban radio probably. So yeah, we look ahead. There's other tabs in here that'll tell you information about the satellites, which we can also look up too. Occasionally there'll be a frequency in here, but there's another place online that has all the frequencies for you. They stay the same though, unless they change them. Meteor M2 actually changed it. It originally was 137.1, and that satellite had some issues when they launched it. They thought they lost it. There was some weird stuff that happened, so they switched to a different transmitter, so they had to change frequencies. So now it's on a different frequency. But and there's an M1 also, but that satellite I guess is it's on a weird orbit, so eventually it's just going to crash, and it's not controlled right now. And you could probably get a picture from it, but it's probably going to be a distorted picture. But yeah, M3, they're launching an M3 soon, so excited for that. And some of these satellites also, they broadcast on another frequency, which requires a whole different antenna, unfortunately. So there's probably other high-res pictures that are on those NOAA satellites, but you almost need a dish to pick them up, because they're going to be in the gigahertz range. Any other questions?
Just as a ballpark, how much does this cost to get into this?
Okay, so this little SDR radio is like $20, and then to make one of these guys from like Home Depot, you're running about 25 to 45, maybe $50 when it's all said and done. And then if you want to get the fancy dancy filter, that's like another $55 or whatever. But like I said, I kind of got obsessed, so I was like, I need that filter. I need it. Ship it down. Add the cart. What else? Yeah, actually, so these antennas today are going to go with you guys, with Star. And I also have 2 radios for you guys. And I burned you guys some DVDs with all that software on here. So you guys can get started and try to get your own pictures, right? Because it's cool. Space is cool and science is cool. And you can do a lot with radio. I'm going to learn a lot more about radio. I'm going to try to get my ham license. Maybe then I can talk to some astronauts on the space station and figure out how to get up there, you know? Maybe they could just see my thumb, right? Yeah.
How do you, so obviously you can't eliminate all of the black lines and the gaps in the pictures if your satellite hardware isn't perfect. But as far as on the sort of terrestrial end of things, what modifications can you make to the antenna to try to minimize signal loss?
So we could try probably that double cross antenna. You won't have to track as much with that because since the poles are on both sides, right? The poles would be like this kind of thing. So then you probably won't have to rotate the antenna as much, right? But you'll have to do math to figure out how long to make this cord that connects to these guys, because it can't be the same. It can't be just any old length, right? So to make a maximum signal, you'll need to do those calculations. Or look online. I think it's online somewhere. Let me see. Yeah, I'm not the first one to do this, so there's a bunch of resources online. And I burned those on those CDs too. So here you'll see, here's an article by Les Hamilton. He's got a great website too that you can go to. And he really drills down into the settings of this app program. And then, yeah, he got a decent picture from his app recorder. Let me see if I can find some other antenna stuff though. All right, there you go. So that is a double cross antenna right there. And you'll see they're not just, it's not necessarily going like this. It's kind of in a weird configuration, like one like this, and then opposite like that, right? But they're different lengths too. And when you wire this thing, you have to do it a special way too. There you go, Lowe's parts list. It looks a little more complicated. They're using copper tubing. Yeah, there's a specific length when you connect these coax cables. There you go. So you'll see there's 2 that are like the same size and then 2 longer ones. Those guys are going to be the delay ones. So the signal will be delayed trying to go through that cable, right? So then when it adds up, so you got your signal wave, right? But you don't want the other wave to come in at a wrong time and cancel it out. You know what I'm saying? Like if you got a wave coming in like this, that would just cancel that guy out and you won't get any signal. But you want to boost your amplitude. So if you delay that signal so that his phase matches up with the other guy's phase, then you get a higher, bigger signal, right? There's a lot of voodoo that goes on with antenna construction and math, a lot of math. And I like math, but it can be difficult sometimes. So here you go, and this guy's using different impedances too, I think, right? No, 50 ohm. There you go. So there's your 4 dipoles, and yeah, those 2 other guys are different lengths. I think he specs it out to what length it should be. It doesn't look like a horrible product, but let me see if I got the quad, the QHF antenna. A lot of people swear by that antenna. Another article by Les. I don't see any antenna stuff in there. Here's the double cross antenna. So there you'll see this over here on the right here is the 3-dimensional pattern for capturing the signals. So it's like a radiation pattern. And there's your circular polarization, right? Because the signals are spinning while they're coming down too. And yeah, there's your dipole. So yeah, it makes this radiation pattern. So your wave at that specific wavelength will, once it enters in here, that gives you like an optimal pattern to pick it up. So, and yeah, this guy, there you go. This guy might be as obsessed as me. He hooked it up to his truck, right? That's my next step. Yeah, maybe I'll just, hook it up to my car. And I thought about that too. I looked up passes while I'm here and I'm like, maybe. Let's see. See me after. I think 9 o'clock or 10 o'clock there's a pass. So there you go. Yeah. Any other questions or? Oh, yep.
Yeah, just real quickly. It seems like there's a whole sort of like online community almost around this, just from like sort of the nature of like the sources and the freeware and such. So, is it just all like really accessible through Google? So I imagine we're going to need like advice at some point as we.
Oh yeah, yeah. There's a ton of stuff through Google. There actually was located somewhere. I think it was in another country. They actually had a little club, and they would upload images and whatnot to this one site or whatever. But yeah, you can find a ton of information online, and yeah. And one of the things that NASA and NOAA is they're big on is that anybody can get these signals. So they really like that a lot. Let me see. So here's a NOAA booklet, actually. It comes straight from the horse's mouth right here, right? You'll see. So they have all these other instruments that are on the satellite doing things, and they're probably coming back on different radio frequencies. But I think in here they actually say. There you go. They give you the lifetime of the satellite. Somewhere they said something about apps. Like ground station or something. There's another thing too with these dishes. If they're passing signals from station to station, you can probably intercept that too if you know where the station is. I saw a guy on YouTube do that too. Somewhere in here though, it said something about apps, and they love that people can do this with off-the-shelf parts. Oh, there you go. So here's all these other frequencies that are transmitting different data. There you go. So apps, there it is, 137 megahertz, and it's amplitude modulated. And here you go. Low cost VHF ground stations. It's very popular in schools. So yeah, there you go. There is a community-based feeling about this, you know, and there is an online presence you can find. So yeah, I also burned a lot of these articles on these DVDs for you guys, so you can go through those and get more info. Any other questions or comments? Or